Last time we essentially produced this graph, except I've updated the data, so we've got, I don't know, maybe 2 or 3 more weeks on here, and I even chopped off another week, just because I didn't think it actually had all the data. So again, this orange is 2020, this blue line is the average of the previous 7 years, and this is the death rate. So this many people in a given week are expected to die per capita. So you can look at this and say, if you multiply that by 1,000,000, that's 240 people per 1 million population in the United States. And so you can see, you get in about 10 weeks, and it's slightly elevated in the U.S. Massive spike, largely driven by in the Northeast a huge spike of cases, and since then it's been coming down. You'll note that most recently cases have been going up dramatically again. I suspect that there's a bit of a lag. There might also be a difference in population that's being infected. There's also possible that a lot of the people who were going to get sick have already gotten sick, or going to die, I should say, are already dead. As this would make it seem as though we're down below, it's possible this data point is still wrong, and that this does not have all the deaths yet that haven't been collected. The data set was current as of July 1st. However, that last data point was like way down here, so I don't trust it at all. Again, I did update the data. What I want to do first is take this graph and try to put some simple error bars along it. And we're going to do this in a couple of different ways. You could try to build a model of what is the death rate for a given week in the US? And you could try to use death rate of your neighboring points, among other techniques. I don't want to get into something that involved anything with this autoregressive kind of feature, this time-based feature. You have to be a little bit careful. I don't want to think about that exactly. I want to treat each week as sort of independent from all the other weeks. So we're dramatically cutting down the amount of data that we have, which is bad. But we can ignore those kind of correlations. So it should be simple. I will do 2 simple things first. This is the average. So we're also going to plot the maximum of any of the previous 5, or however many years, maybe 7 years, I think, and the minimum. So that's going to be super easy to do. And then we'll try to compute a simple t statistic, assume that the death rate is normally distributed, or I should say students distribution distributed, since we have very few data points. We'll try to do that. If we don't have that, if that doesn't work out so well, it is what it is. Again, if we had 20 or 30 data points, 20 or 30 years, then I'd say don't worry about it. We'll just do normal, but we really don't, so we should do the proper thing. So we'll keep this in mind. And instead of the mean deaths, let's come down here. And I've already loaded in all my data, so that's convenient. Let's compute the max deaths right here. So it's going to be exactly the same as before, except instead of mean, we're going to say max. And we'll similarly do min, just like that. And grab this on here. I'm not so worried about how this looks exactly. I added the actual points themselves, just so you can see. But I'm not as concerned about that for just these little error bar like objects. Come on. There we go. And let's get the min. And let's just real quick see what that looks like. Okay, so again, the green is the maximum, the red is the minimum, and this should also tell you some interesting features. Now, these are not the error bars, right? This is not like a distribution. Other than one driven by the max and the min, which there are distributions that do that. It is entirely possible that you can exceed the previously seen max, and that's not that exciting. Because, you didn't see that many data points, so how interesting is it really? That kind of thing. Okay, this is super cool, though. I dig this. So again, orange, current year, 2020, death rate. Blue, average of past 7 years. Green, maximum over the previous 7, red, minimum over the previous 7. And so you can see, the huge spike at about, week 14 of the year? So that's sometime in April. And coming down since then, thankfully. Although we'll see if this ticks back up. Again, I don't know that I trust this point. 1, and 2, note the scale. This does not start at 0 down here. This is an isolated view. If you wanted to force it to start at 0, then you would get less. You wouldn't be able to see as clearly what's going on here. So you'd be making certain trade-offs. But the fact that this is below like that minimum rate is a little suspicious to me. A little bit suspicious. But I want to compute the t statistic. So if you were doing something normal, you might just say, oh, well, I'll just take the standard deviation of death by week, axis equals 0. And you can just do this in NumPy, and it's like as good. However, we don't have very many data points because death by week, I have 6 years. You're building a whole distribution off of those 6 years. Not a lot. I mean, if we had, 30 years, that might be good. Even then, it's probably driven by other factors. So let's look up students distribution. Students distribution. Show me Wikipedia. Yes. Ad-free. Pretty easy to understand. And it's mechanically, we're going to use it similar to how you would use a normal distribution, but note that it's flatter based on how many data points you actually have. So we have like 6, that's actually pretty close to normal, depending on what it is you're looking at, that kind of thing. But again, if I had like 20, I would say, yeah, screw it, it's fine. Students' distribution arises from sampling, yada, 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 yada. It's a standard normal distribution. Wait, hang on. Random variable blah, standard normal distribution. And the random variable blah, where S has a student's t distribution with n-1 degrees of freedom. Yes. Okay. So let's compute that variable where S is the standard deviation of the sample, not of the population. If we knew the population and standard deviation for these deaths, we could use that. So I'm going to call this my t value is going to be, let me think about this. That's the standard deviation along each axis. Mean death. Hang on. It's how much above the mean are we, how much below the mean are we. Right, I'm not looking at a particular number. I need a scratch pad. I need McGimp. That's what I need. To illustrate some concept I'm thinking of here. Yeah, these things are all fine, whatever. Oh my gosh, make that much smaller. Yes. You've got this, oh, that's terrible. Airbrush mate? Pixel. No, jeez, oh man. What is going on with this nonsense? Why is it, oh my goodness. Mode, normal, dynamics, basic. No? Can I just turn this off? None? This is horrendous. Oh, no, I don't want, I just want the pencil. Oh my gosh. Basic, simple. Thank you. Oh, that's what I want. So much better. Anyway, you got your distribution, which doesn't really look exactly like this. It's got some mean, which should occur better thereabouts here. There's your 0 point, or your, yeah, that's where the mean occurs. This sort of distance is driven by 2 things. How many degrees of freedom you have, how many data points are you looking at, and what is your standard deviation of this data. I don't want to look at a particular data point and say, all right, well, given that I had a data point over here, how likely is it that it came from this distribution? Or like, usually you say a data point there or greater. And so you say, what is the area of the curve from this point on? And maybe sometimes you're interested in like, well, what is the area of the curve? It was plus or minus this much. Where this much, is, maybe that's 2 sigma, we might say, or 2s in this case. And minus 2s over here. So really, we want to compute this number. Except I want to compute this number for a fixed amount of area. I want to fix that amount of area at, I don't know, 5%. So if we were doing a normal distribution, this would give you about, this would be the typical like 95% confidence interval is what it would typically be. But we don't have that. We have the students distribution. So let me come back to my over here. You can get all this probability density function, whatever stuff. You don't want to compute this manually. Let me just say that right now. You don't want to do that. You want to use an existing method to compute that, like numpy.random.student. Hey, what do you know? Student. What is student normal? Draw samples from standard normal distribution. Oh, standard normal. I misread. Standard T, is this? It's also known as a T-stat. Yeah, from a standard student's T distribution with degrees of freedom. Yada, 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 yada. So this gives you a bunch of data points. And again, it's degrees of freedom and how many? Yeah. So this will create a bunch of data. If I say, yeah, give me, I've got, like we have 6 degrees of freedom. Size equals, I don't know, 10. This generates those numbers, right? It's not exactly what I want, though. I don't want to generate numbers. I believe I need to import scipy.stats as ss. ss.random randint.student. Okay, .stats. Okay. Oh my goodness. Is there a student? No. Is there a T-stat? Interesting. T standard. Trimmed? No. Okay. We're going to look this up then. SciPy students distribution. Yeah, SciPy student confidence interval. Yes, that's what we're doing here. Wow, that's some weird mathematics stuff. Oh, just T. Okay. So this can tell us exactly what we want. The location, this is going to be our mean. The scale, this is going to be that standard deviation we computed. This is our degrees of freedom, almost certainly. And this is our 95% confidence interval, whatever it is. Or you want 99%, and this will tell you how far you need to go out. So note here, interesting, it's not exactly symmetric, which I thought it was. Am I misunderstanding? Oh, no. I misread that. This is based on location. Okay. Let us grab this then from scipy.stats. No. I'll import scipy.stats as ss. And then ss.t. Yeah, there we go. Dot interval. Okay, that is, I think, the one we want. Yeah. So if I said I want, 95% confidence, I have 6 degrees of freedom. Suppose the location parameter was 0, that the mean is 0. That's not the case. And that the scale parameter, the standard deviation, was 1, just for the sake of argument. Now it gives you sort of symmetric values. That is, of course, not what we have. And we need to compute this for each of our little points. So our t values here. How do I want to do this? I want to say ss.t.interval. Yeah, let's do 95% confidence. We have 6, I believe. Hang on. Death by week dot shape 0, right? Death by week dot shape. Yes. Just to make sure we're trying to be sane here. And location, that's going to be equal to m. Scale is equal to s for m comma s in zip. And that's going to be zip mean death and oh shoot. We'll call this scales, I guess. So I get for naming things that way. So this will make that interval the top and bottom for each one of these. And what I'm going to do is convert this to an array right away. I have to do this silly little list comprehension. But we can do this. We got our scales there. Let's run this and see what happens. T. Okay. And now everything in the first column, those are our minimum values. Everything in the second column are our max values. These are the actual rates themselves. So what we can do now we can actually plot these. Now we can plot T of all the rows, comma the first column, our minimums, and T of all the rows, comma our second column, the maxes. And now, and that's the brown and the purple here. So you can see the max and min are well within those bounds, which is good. And they're just a little bit wider than those. But you can see clearly at the start of week 12 of the year, so it's the very beginning of April, you can see there's pretty clearly you're beyond the 95%. You can compute, if you wish, exactly for that given week, what is the probability of seeing this at random, or like given this distribution, I should say. And you can continue. You could do that for all these if you wanted to do so. I don't think that's super relevant here. What we wanted to show is like, well, all of these are above that, which is curious. Now we've done a bunch more than 20 little points here, right? We got up to 23 odd weeks. Let's do the same thing, except I want to have a tighter, let's call this T2. Woo. A tighter set of, or not tighter, a more broad interval. So we'll say, everything within 3 nines. So, that's like 1 in 1,000 if it's outside that point. That could happen given this particular distribution. Now, we haven't actually checked, does this data actually look, vaguely students distributed? Yeah, that's a very good point. We have not done that. Now you see this gray and this pink line, and the pink line gets rather small, and this line actually, about 3 nines over here. Once you're on week, what is this, 13? Yeah, then you're, this is going to be ruining models forever. Forever, probably. At least for 100 years, in terms of like modeling death rates, things like this. We could plot specific other specific years as well, but I suspect it's not going to be super duper interesting. Okay, we can do this for all the United States. Now, we could also try to do this for each specific state. And probably what I'll try to do is pick a state to start with, make sure I can do the same thing, and then come back and turn that into a function so I can apply it to any state. I'll apply it to all the states, and then we'll look at some of these data points bit by bit. I suspect what I want to do is have the mean, have the plus and minus 2 standard deviations, and the 2020. So that sounds like 4. That's four numbers we want, not 4 numbers, 4 lines, 4 series for every state. I'm trying to think of a good way to plot these now. Yeah. This is already, you could encode this like in a heat map itself, but I want 50 of those heat maps, oh man, like across the like actual plotted out map of the state. You could try to plot each one of these, or like little spark lines sort of thing. That would probably be the right thing to do. Plot this 2020 thing as a spark line with these other little error bars for each map, for each state. But, okay. Let's do for a particular state. So let's choose New York, since we know that was a big one, and then we'll do another state to compare, and then we'll try to generalize it to any state. So the pickle that we're in here is, I have death by week. That was a very convenient thing I made for myself. Where did I make that? This thing. Yeah. So this is death by week, which is derived from US all death. US all death, oh boy, is the concatenation of all these things. Okay. So need is to grab this, and I'm going to change everywhere there's US to be NY. New York, New York. And I think what we're going to do is, oh boy. This is what I get though. All causes. All Kanye. Yes. All Kanye all the time. All causes. Okay, perfect. All cause, not all causes. Yeesh. Instead of United States, we'll say New York. And I will verify that it is called New York in here. Yes, it is, with a space and everything. Perfect. New York. Okay. Let's see what happens here. NY all death. So these are absolute death counts by week for the state of New York. Why is that so high in that week? That's wild. Let's just plot NY all death. Didn't I? Oh. There we go. NY all death. Okay, similar kind of thing, much more drastic here, you'll note. Also, I feel like the general upward trend, oh, I guess maybe New York's population has not grown that much in the last 7 years. Perhaps other parts of the United States have grown significantly more. So that's interesting. Okay, yeah, same kind of thing. Also a lot more jumpier because you have fewer data points, fewer things to average it out. Same, this kind of spike here a couple years ago, 2018. Don't know what that was. I wasn't here. Okay. We'll look at New York death by week. This is New York. Okay, but we need to get a new estimated population, right? We need, oh boy. I need the state population based on the states here. States. Yeah, what is in my states array again? I do not remember. In all honesty. States.columns. States.name? What is in this? Show me New York. Okay. So states, where states.name equals New York. Just pull out that row for me. Really? Oh, son of a gun. Seriously? What is this nonsense? New Mexico, comma, New York, comma. None of are in the columns. Oh, I see. Not the problem I thought it was. There we go. Well, that's the average population, what, in 2015 or something? Not quite what I wanted, but we have to use this to try to estimate our population at that time. Just convert this to a list, just so I can look at it. Not what I wanted. What if I do this? What is A? Type of A? A of 0? No, of course not. I just give me the data. I want to see it. I don't want to have to like reach into the columns. That's why I wanted a list. Oh, what a mess. I would have solved this right now. Pandas extract row. Just give me the row. Convert row to list. Just give me the list. Yeah, fine. List of lists. I don't care. Already asked. Dot values dot to list. Okay, that's what I wanted. A dot to list. There's no option. Oh, what? Oh, dot values. Things that. See, this is what I should have gotten when I called list on the object. Okay. Anyway, you got 2015, or sorry, 2000, 2005, 2010, and 2015 estimated. And of course, 20, what is this number then? Oh, it's the average over those years. Right. So what we need then is a way to interpolate beyond the given dates. One-dimensional piecewise linear interpolant function. Yeah, that's the problem here. Because if I say numpy.interp of, let me just, what does it want? It wants the dates first. Okay, whatever. 2000, 2005, 2010, 2015. And then it wants these numbers. And again, we're just doing this real quick just to see how does this actually work. It gives you a function. One requires f function pointer. What? Hang on. Dates. Index years plus 0.5. I misunderstood how interp works, and I'm sure I had the same problem last time. Coordinates in which to evaluate the interpolated values. I thought this gave me a function that I could call whenever I felt like. Is there a similar thing? So it does not return a function. Okay. Sequence XP. Okay, never mind. Never mind. So the points where I actually want to interpolate. Show me 2020. Show me all these points again. Also show me 1995. All those points in 2020. Right. And this is the problem. Right, it doesn't actually, I want just a simple interpolation, like take these two and go beyond. And yes, I could develop such a thing, but I don't want to have to do that. NumPy interpolates beyond data. Well, maybe SciPy is what I want. Call method uses interpolation to find the value of new points. Class returns a function. Ooh. So maybe that's what I want. Let's just import SciPy. SciPy.interpolate. What is it? Interp1D. Kind. Yes, you can do linear. You can do other stupid simple things. I will just be doing a linear, just to make my life simple. And the x's and y's are exactly as I had before. Cool. So, yes, 2000, 2005, 2010, 2015. And then these numbers, this should give us a function then. Then if I say f of 2000, should be dead on, great. If I say f of 1995, the value in x new is below the interpolation. Oh, come on. Bounds error equals none. If true, value is raised in intelligence and tempted value outside the range of x. If false, out of bounds errors are assigned failure, but if false, error is raised unless build value equals extrapolate. Well, of course I want to extrapolate. If extrapolate the points outside the data range will be extrapolated. Well, yes. That is pretty clearly what I want to do. This is what fill value equals extrapolates. And then we'll say f of 2000, f of 1995. Oh, geez, not that much. You know, just give me something vaguely reasonable. Sure, that's great. I mean, just plot that plot of f of x for x in NumPy.a range. Woo! 1995 to 2025. Something like that. Yeah, that's super great. There's a bend, it's perfect. Yeah, that'll do perfectly fine for our purposes. Okay, so all that nonsense. It was just to get this estimated pop thing is what we want to build. So I have this states array. It's like now I need to go back. That's the way in which we actually will make this work. Let's come back up a little bit. Import scipy.interpolate as si. Right, so we'll say si.interp1d, and I'm gonna put some stuff in there. Oh, remember, we'll say fill value equals extrapolate. Doesn't need to be perfect, okay? Just some simple things. I didn't know SciPy had this interpolation. That's super cool. How do we form estpop? Estpop is literally just the interpolation among the years of interest. So this is how we make our function. These are the dates that I want to compute it on, right? These are the dates, the times at which we are claiming we had the values. This will be index years plus 0.5. Then what are those actual values? And this is where we pull in, oh geez, what a mess. There's going to be states. Okay, let me make a population counter for all the states. It's like I sort of need to transpose this matrix in a way. No. Let's. Yeah, I need to just extract that row though. Right, problem is I have this thing states. And sure, I can say states of, what is it? Population 2000, you know. We can do this. Great, but now, now I need to get back to New York. I need states of population 2000. I need states of state.name equals New York. States, plural, of course. That's what you need. But it's like I need this a bajillion times. So what I'm gonna say is just call it pops. Not pops. sinfo. Just for this specific state. So we're gonna be referring to that multiple times. And here what we say is sinfo of population 2000. And then we're going to do almost the same thing, but 2005, 2010, 2015. If I can fix my... Okay, clearly I've goofed this up a bit here, but that's all fine. Okay, perfect. And by perfect, I mean, that next bit is done. 15. What was it exactly called again? 2015 est. Because you got to get it exact. There we go. Okay. Do that. Great. We have this. That didn't work. Why not? Probably some key error. sinfo population. All right, what's sinfo? 10 columns. Did I spell population wrong? Population 2000, 2005, 2010, 2015, est, right? Tell you what, let's check each one. What? Son of a, stop it. Stop it. 5, 10. Each one of those works. So maybe it's just an auto indent problem. These kinds of things happen. No. Still lying to me. All right, let's take a look at PDB. What's going on here? Let's go up a few layers. Okay. Where are you actually complaining? Oh my goodness. It's a problem within the interpolation. Is it not fill value? Is that not? Fill value. Extrapolate. Extrapolate. Let me grab it here, you know? 1, 2, 3, and 4. That's no problem at all. IDX years? Plus 0.5? Oh, that's not right. I see. I see the problem. This is not the right thing to be using. Because that's the points at which you compute it. Yeah. What is dates? I think dates is probably the things I want. No, dates is where I want to compute it. Dates. Right? Yeah. What is US pop? Oh, US pop was longer. I had more data. Duh. IDX years. Yeah. IDX years is not the right thing at all. IDXS years is equal to numpy.array of 2000, 2005, 2010. I'll just say numpy.arange, make my life a little bit easier. From 2000 to 2020, check by 5. There we go. And then we'll add, that was a problem. Now, still a key error. What is the problem here? Like, this is a super unhelpful error term here. IDX S years. There's 4 things there. Can you not do this? si.interp 1D. Do I have to say the kind? Kind linear? No, I have plenty. Does that have to be an array, maybe? Array-like. An ND array of real values. The length of y must be equal to the length of x. N-dimensional array. Interesting. I would like to see an example. No, you just totally use a one-dimensional thing here. That's fine. F equals x and new. You interpolate a bunch of things. Yeah. That's odd. Yeah, that's super weird. Okay, SciPy interp. Yeah, let's see if this is something. Interpolate key error. Like, surely it's someone else's. Multiple key string interpolation in Python. Key error 2. What? That's not at all. This doesn't have SciPy in it, does it? No. You know, I want all of these terms, Google. I was very particular. If you don't have it, you don't have it. Oh, this looks similar to what I got. Treat error, SciPy, and Python, converting Python, yada, 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 yada. Well, this is super weird. I don't know why it's having this issue. I can only think. All right, well, let's eliminate possibilities. Is it that? No, it is not that. Okay. Is it that maybe my populations are a list? Maybe that's the issue. So let's turn them into an array. Come back here. S pops. Let's do that. Maybe that'll work. Come on. Stop it. Really? Okay, so it's not SciPy's fault. That's good to know. Like, what is literally the problem here then? This makes no sense. Like, I can freaking copy paste right here. Boom. Oh, it's not a number. I see. 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 What if I do this? Then I can't get it because it's pandas. It is not really what I wanted. That values. Really? Wait. But it's not an ND array. That's the problem, buddy. That is exactly the problem. That this is not actually an array, is not actually an integer. Yeah, what is this, pal? The series, whatever. Oh, great, yeah. I don't need the index. Okay? Therein lies the problem. What I want... Just give me the top value. Yeah, okay. Can I just say int of a? Okay. Things that don't need to be this complicated. Again, pandas, super handy, puts distance between you and your data, though. And that's where problems like these tend to crop up. Anything that puts distance between you and the data. These kind of abstractions, they're powerful, they're necessary to a degree, but these kinds of oddities will happen. Where, like, why is this error happening when if I just had all my data and I was in C or 4chan and I had to handle it all myself, I wouldn't have this issue. Now I'd have a lot of other problems. But, okay. So my NYS pops then. This is US all death. This should be length of NY all death. Week. What is week? Okay, yeah, that stays the same. This, that should be the same. Instead of interp, we just call it F, and we just call F on the dates. Can I do that actually? Oh good, it vectorizes. That's awesome. And so you can see, the estimated current population of New York State is about 20 million. Oh, sorry, that's getting us all the way to 2021. I will say population New York State. 19.5 million. It's flattened off. But okay, so it's maybe a little overzealous in its estimates. Wait a minute. All these numbers are bigger than 19.5 million. What? Huh. Well, that's interesting. Whatever population this has is bigger than whatever that is. Okay, that's fine. Point is, I don't really care. this is good enough for our purposes. That is exactly a line? That is not quite what I wanted. Okay, maybe I did want a simple spline. Spline? Is S linear, spline linear? Where? 0, S linear. Spline interpolation of 0, first, second, third order. Okay, that's what I wanted. My own fault. Let's redo that. Kind equals S linear. So rather than fitting a line to all the data, we're just going to go in between each point. That is so curious. That is super suspicious. I don't like this. I don't like that at all. Did it make a new F? Did it actually do that? I'm not convinced anymore. Was it S quadratic? I want to see some change. That's all right, that's not a thing. si.interp1d. Cubic. Okay, fine. Just give me a cubic or a quad. I want to see a change. I don't actually want the cubic. What is going on? I have enough data to do this. What? This is hot garbage. Hot garbage. Okay. Is straight up spline an option? Spline over 0, first, second, or third order. Previous or next value. What? You did not give me a spline interpolation, pal. I am pretty sure you didn't. Granted, I'm using 4 whole data points here. But I still think. Yeah, look at this. Okay. Should be some kind of change here. Should be some kind of change. In fact, let us IDX S years, just so I got it on there. Let me plot of dates. Oh, no. Let me come back. S linear, right? There we go. Do that, and then we'll say plot of dates and NYEst pop. So put these two things on top to do what? Okay, that would explain a lot. I have data over here. I'm computing all my numbers over here. Well, yes, that would make sense then. It's fine. It's fine. If I could get a simple population table going back to the last 7 years for every state, I would do that. This is fine. This is fine. It's we don't care. We don't care. It's totally fine. It's all good. We have New York estimated pop. We're going in here. We're doing it. Boom. Look at that. We did it. NY death by week. Death by week. Boom. And this is the rate of death by week. Let's just plot that real quick. Come on. Not the shape. The actual thing. Oh no, what'd I do? That's not what I wanted. That's not right. 6 over the years. I see. So, what we want is to get this stuff for New York. Grab all all that. Come back down here. NY specific. So we're going to add some New York stats on here. I do want the mean death. What is this nonsense? Death 2020. Oh, yeah. This should be NY all death and NY est pop. Get NY. This will be NY as well. Okay. I don't want the max and the min anymore. I don't need to re-import things. I do need to do this again. NY death by week. Do that over here. NY. 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 I don't need two sets of these though. Okay. So. I said this is fine. I don't care. Plotting the mean deaths of the previous years. Plotting 2020. And plotting the bounds on those. Let's see what happens here. Okay. Yes, so we got the same kind of chart here. And you can actually see how things are going suspiciously low, for example, here. Counts. But you can see how in New York, you see like a huge, massive spike, which is, you know, interesting. If we pick a different state, we will see something different. So let's functionize this. It's a little bit of a mess. I don't know, plot state. Plot state. And we'll say ST is equal to New York, is the default option, of course. Do that, except wherever we say New York, we're going to put ST. Should just be these handful of places. Okay. And then what I actually want to do is return. What are the things that I want? It's like I want these 4 series. New York mean death, New York death. Let me get New York death 2020, New York mean death. Do I care to have the... It's like I could always rebuild these if I wanted, right? No, I could not actually. And T. So we'll always return those. Let's do that. Perfect. Now is my figure still up? It is not. Okay. Now we will plot dot. Here's what I want to do. States. Yeah. Okay. States dot name. I have 50 of them. Perfect. I was also worried about that. Oh shoot! No, I have 51. Curse you, District of Columbia. I think, however, that DC is going to be in there. U.S. death 2020. No, that's not what I wanted. Data. No, I should just go look. Columbia. Yes. Okay. Spelled out the same way. For ST in. What are we doing? We are saying states.name. Say plot.figure. Plot.title of ST. And we'll plot dot. And we'll call plot state of ST. Is that what I called it? Yeah. Okay. Cool. So let me just real quick try something. Plot states of Ohio. Okay, so Ohio had a spike, but not so far beyond its typical numbers. Above 95%, definitely. A bit of a dip here. That was more in line than you expect, really. Okay, and let me just do another state. District of Columbia. Yeah, they got hit real bad. Same kind of problem. Okay. Let's take a look at Washington State. They have it a little earlier, of course. There's a lot jumpier because there's fewer people, naturally. I'm sure if you look at South Dakota, jumpy. Yeah, this makes me think this data's suspect these past few weeks. Very curious. Very curious. Anyway, let's plot all these states. I'm going to be plotting 51 things. This might take... Like, the actual plotting is the most expensive part of this equation. See if they show up or if I crash my computer or something. You know what? I should have made like a subplot of all the things. It seems like these are not actually showing, unfortunately. Too many matplotlib tokens. Yeah, that's cute. What I need is I need to put a pause in there. Oh my gosh, stop. Oh boy. Okay, there we go. Now it's going. Alaska. Alabama. Arizona. Actually elevated and still elevated. Arizona, of course, one of the hot spots today. Arkansas, not that exciting. California, dipped and came down. Colorado, big early on. I did not remember that. Connecticut, this is so weird. Did the people die off already? This is the strangest thing. That is so low. Like, we're almost coming out ahead if you believe this. That's so suspicious. Delaware. Pretty typical. District of Columbia, again, typical East Coast shape here. Florida. Cases have been rising dramatically in Florida. We'll see what happens to this. Death rate also just overall noticeably higher in Florida, probably due to their older population. Georgia, way down on the deaths again. This is just, I did not expect to see this. Hawaii, they've kept it under control, notice. There's a slight spike early on, probably because they have more travel with Asia, but then they've kept things under control, almost completely. Idaho, not very populated, they're doing all right. Illinois, huge problems. Obviously, they're not even down below here, so maybe I trust these numbers. Indiana, similar to Illinois, but again, this huge dip. I just do not trust that one bit. Iowa, Kansas, Kentucky, this just doesn't make any sense. Why would it be normal and then way low? That to me is just so suspicious. Louisiana, same story. Any place with a major city? Yeah, Maryland, of course, Baltimore had a big. Massachusetts, Boston, Michigan, Detroit, Minnesota, Minneapolis. Mississippi actually also was kind of big. Also, much higher rate overall. Again, that's another interesting thing. We should plot that in a choropleth, like the average death rate for states. I'm sure you'll see some interesting disparities. Montana, okay, I just don't trust these last 2 data points. Let's just throw those out. There's no way I'm going to believe that. I think some states are probably just better about, what is this huge deviation? On January 1st. Wow. Utah, it would appear to be under control. Also, Utah appears to be good about reporting their statistics. Vermont, low population, so that's why you see these jumps. Virginia, again, I suspect some states probably just lag behind by as much as a month, particularly when there's been more deaths, just taking them longer to process them all. Washington, I guess I get to do all these. West Virginia, way down. West Virginia was one of the later states to get anything. Yeah, they have to be a month behind. This is so incredible. It's like we can't even analyze this data in terms of on a per state basis, really, until like 3 months afterwards. It's just the states are this far behind in showing. Now, granted, as more people die, if you have a huge spike in deaths, your population is actually lower. But as long as that's a small fraction of the population, it doesn't really matter. And Wisconsin. What is going on in Wisconsin? This I have not seen before. Where there's these huge dips, or sometimes spikes. The standard deviation, okay, it's huge dips, but that just means the standard deviation is huge. What is going on at like week 8? This is like the Super Bowl? And do people like cling to life during the Super Bowl? And then week 30? Like, I don't even understand why. What is it? This is like week July or something? Yeah, 57. That's July. What is this, July 4th? Wisconsinites go nuts, and I feel like this has got to be like some weird coding error. Like there's some holiday around here, some important holiday, and so they code to this after that or something. That is so strange. Or do people just not live there during those times? Anyway, 2020, elevated overall. We have reached our time limit for today, so I think that's all I'm going to do. I'm glad we were able to plot this, compute the actual t-stats, even though we did not demonstrate at all that this data follows a t-distribution. That's just a reasonable thing to take to try. Glad we were able to do this for each state. I don't think the data is actually clean enough to use in general. Several states are just like a month behind on reporting their death statistics. Maybe they're trying to game the system. Probably they're just behind. Because normally, it's not that big a deal. It's like probably, if you were a researcher using death statistics, yeah, like whatever. I'll use everything from last year. Then I know I got it all good. You're not worried about getting the death statistics from last week, which is what this is. So I suspect that is what we're seeing with those numbers, which is curious. There's some states you can sort of trust that are very quick and some that aren't. Next week, we will be back. We'll be looking at a similar data, but from the United Kingdom. And so what I'll want to do is compare and look and see how are their numbers different. Did they see the spike? Does the numbers look like they're coming back? We don't see that here, probably because the death rates, the places that are good about reporting their deaths already had their spike, is my suspicion, those East Coast states. Other states, not so much. Also, we plotted way too many data points here. That is all I have for tonight. Thanks for watching, and don't forget, stay safe in the data mines.